Alright, welcome back to Meteorology 101. This is the second part to Atmospheric Physics 2, and we're going to be covering thermal winds. Alright, a thermal wind vector is useful for a forecaster in a remote area without centralized charts. You can get a lot of information from this wind, but it is not really a wind at all, and we'll cover all that. So the thermal wind vector, B sub th, thermal wind, is a calculated wind, non-existent or theoretical, found by computing the vector difference of geostrophic winds at two levels for the same location. So we're using an upper level wind. So the thermal vector equals upper level wind minus a lower level wind. Take those wind speeds minus those and direction, and you can come up with a thermal wind vector and determine a lot of stuff from this. When we talk about a geostrophic wind, we're talking about, on a geostrophic scale, the right above the boundary layer or a standard atmosphere, that the isobars on the surface determine on them that spacing with no outside factor like friction or anything affecting that wind. This chart is 100% accurate of what the wind speed should be. So if we look at a surface chart, we can see the isobars, and then the wind speeds, depending on, we know winds circulate clockwise around the high, counterclockwise around the low. So there's our direction, and then the tightness of these isobars will indicate the speed of that wind. So we measure across the isobars with that geostrophic wind chart, and we can determine the wind speed at the surface. Now on the surface you're going to have friction, so that's going to slow and back the winds, so you're not going to be 100% accurate. That's why typically we go to about just over 300 feet and get out of the that area of friction above that boundary layer, and then we can use that geostrophic chart to determine the wind speeds there. If you don't have a station showing you the wind speeds indicated on these charts. So if we go, let's just say Columbus right here, that's reporting about looks like a 15 or 20 knot wind out of the northwest, and then we need to look at the thickness of these isobars. Go to our chart, and based on latitude, so 40, we're at 40 latitude. That line right here that basically cuts the US in half is the 40-degree latitude line. So we're going by 40 degrees. Here's our 40, point A to point B. Anything below that is really insignificant, 6 to 10 knots. Anything above 10 knots is when you start getting into a significant wind with the isobars. So if we look at our thickness of the isobars, right there across Columbus, look at the chart, we are pretty much right between the 15 and 20 knot wind. So that's pretty accurate on this surface chart. So that's what we're talking about on geostrophic winds. There's a geostrophic wind scale that will give you the pretty accurate wind speeds on the surface. If you just only had the surface chart with no station plots, or you're missing station plots, can't determine that wind, you can use that scale to help you out. So the magnitude or length of this vector is proportional to the strength of the mean temperature gradient within the layer, the thickness packing. So we're going to go to a thickness chart and look at that. Now the magnitude is how strong it is, or the length of the vector. So we'll cover that here in just a second, put a visual on that. The direction indicates the orientation of the thickness lines, with cold air to the left and warm air to the right, or with a thermal wind to your back, colder temperatures to your left. So get into a chart here. Now if we go with get my pen up, if we go to with the wind to your back, the cold air is to your left. So we take two different heights, 850, 700. The strength is the same, 20 knots on both heights. The direction is slightly off, slightly different, so we're backing with height. So we take our location, take the 850 wind, that's the lower wind, plot the direction, and then the magnitude is your speed. So we got to determine what this line means for magnitude. So if we take, say, 280 degrees at 20 knots, this is going to basically, that line is going to be cut in half if you just estimate 10 knots per line. So now you're at 20 knots. So say this is a half an inch, that one's a half an inch, and then we see our wind speeds at 700. Now we're at about 260 at 20 knots, so we're the same length, so we're still going to be, 1 inch total for the magnitude, 10 knots per half inch. And then just take a line and draw from the tip of the lower wind to the tip of the upper wind, and then measure that. Now this isn't quite 1 inch, say, let's just go 3/4 of an inch, so we're going to go about 15 knots. We're going to just say that's 3/4 of an inch, so half an inch is 10 knots, and then 1/4 inch would be 5 knots. So if we go half inch, 1/4 inch, that's 15 knots total. So our thermal wind is approximately from 350 at 15 knots. Now, like I said, that's a theoretical wind, parallel with the packing, the thickness packing. It always travels parallel with the thickness packing. But what you're going to get out of this is, with these heights, the two different winds backing with height. So the 850 is from the northwest, 750 is from the southwest. So our wind is actually backing. So now that is an indication of the cold air advection. We'll get into that in just a second. So that's how you calculate a thermal wind with a thickness chart and based on those wind speeds. Just use a SCOOT chart at a certain location, and then you can see pretty much right away if you have veering or backing with height, and then you can indicate what kind of a temperature advection you have. All right, so here's a thickness chart. We have the surface pressure, with the isobars, and they're crossing the thickness lines. Now the thermal wind would be, depending on which way this is flowing, but you can pick your jet stream out of that thickness. The tightest thickness packing is about to place under the jet stream. So weather always travels west to east, so we could say that our thermal wind is going from the southwest. So now to calculate that, you just take you'd have to have a SCOOT chart and have the lower level winds. You want to calculate upper level winds. Doesn't matter which levels, 850 to 700, 700 to 500, it doesn't matter. So then you determine what you have for your magnitude and what your thermal wind is. Like I said, it's a non-existent wind. You're just trying to determine, do you have cold air advection or do you have warm air advection? That's your main goal using this thermal wind. Okay, so we can pretty much look at this. Winds travel clockwise around a high. We have lower heights, the colder air to the north. There's the 540 line. I always make that one purple. I customize these charts with colors. So that's our rain snow line. And then we get into the warmer air. and that would be to the right of the thermal wind vector. So we can say we got cold air advection going on right there. So if just using the thickness chart, there's so much information you can get off of this. We'll cover the thickness chart in the next video. Right now, this is just an example. So here's our thickness lines. The tightest part of those thickness lines is indication of a jet stream, and then you get the thickness lines crossing the isobars on the surface, so you can determine if you got cold air advection or warm air advection. That's mostly what we're going to get out of these charts. All right, so the observed winds above the gradient level. Now the gradient level is pretty much or approximately geostrophic. Commonly used to calculate thermal wind vector rather than determining the geostrophic wind at each level. So you don't have to determine the geostrophic wind at each level, but the observed winds at the gradient level, that's approximately 1,000 millibars, right above any of the surface friction. So the interpretation, winds varying with height indicate warm air advection in that layer. Winds backing with height indicate cold air advection in that layer. So if you're going from the 850 to the 700 millibar, you're going from approximately 5,000 feet to 10,000 feet. So between 5 and 10,000 feet, these winds are veering. So that's an indication of warm air advection. If they were backing, winds are further out of the northwest and then going westerly. Now you're backing, the winds are backing this way. So with height, these are veering. So the wind barb is going clockwise, that is veering, counterclockwise, that is backing. And with backing, you indicate cold air advection and warm air advection with veering. So that's one main thing to remember when you're looking at these upper level winds. So if you pull a SCU T at a certain location and you expect, severe thunderstorms, supercells, but you have winds veering with height or backing with height, let's say cold air advection going into that area, then cold air doesn't hold as much moisture as warm air, so it could dry that supercell out and actually bring it back down to a, still be a cumulonimbus CB thunderstorms, but keep it from going severe and creating tornadoes or large size hail. That's just a indicator to use for if you're a storm chaser. Alright, so the characteristics, like we said on the thickness chart. So thermal wind vector is parallel to the thickness lines, just as winds are parallel to the isobars. So the surface winds are going to be parallel to the isobars on the surface. The thermal wind is going to be parallel to the heights, the thickness lines on the thickness chart. So with the thermal wind being parallel to the thickness lines, the cold air is to the left, warm air is to the right. Within the boundary layer, friction causes the actual winds to veer with height and may not accurately indicate advection. Therefore, it's best to use the winds above 3,000 feet. So, in the boundary layer, the actual winds, friction causes the winds to veer with height. So, the reason for that is on the surface, the winds are actually going to back. So if you have the winds from the southwest on the surface and they hit that friction, they're actually going to go more southerly on the surface. Now in the upper layers above that boundary layer where there is no friction, if you have that southwest wind, even if it's the same, now you are veering with height because you're backing on the surface, so that causes veering with height. Alright, so use winds above 3,000 feet to get out of the boundary layer. I mean, pretty much you're saying 3,000 feet because you're, the mountains and all that. So you can even go, if you're in Colorado, you probably want to go more, 5,000 feet to get out of all that friction. But with the thickness chart, you have a cold pocket. What we can do right here on this chart with the thickness lines and the surface pressure is we know winds circulate counterclockwise around the low. And we have that cold pocket. You have lower heights to the left, the cold air. So now with that wind blowing across those thickness lines and having lower heights or cold air to the left, then we have cold air advection pretty much all in this area. So then you can use that to pretty much determine where your cold front is. Coming out of that low, everywhere there's cold air advection. So you can determine your cold frontal placement. You can determine the tightest thickness packings. You can actually determine where your jet stream is. So the north-south temperature gradient, this isn't a real great example because these are closed heights, contours, but the tightest thickness packings is where the north-south temperature gradient shows up for on the thickness chart to determine where your jet stream is. Just another tidbit. We'll get like I said, we'll get more into the thickness chart in the next video. All right, stability. So when we're determining these cold air advection and warm air advection with the heights, we can go two different layers and then we can determine the stability of the atmosphere. Cold air advection under warm air advection, that would indicate stability. So it's warm over cold. We discussed this a couple videos ago with stability of the atmosphere. That's the cow is unstable, so cold over warm is an unstable environment. Warm over cold is stable. So warm air wants to rise, cold air wants to sink. If the cold air is on top, it wants to sink. Warm air wants to rise from the bottom. It is an unstable environment. If warm air is over cold, then the warm wants to go up. The cold air wants to stay down. So everybody's happy. So it's a stable environment. Warm air advection on the cold air indicates decreases stability because the density of the air decreases at the surface and increases aloft. Therefore, changes in atmospheric stability can be determined from the wind field. In the vertical, use SCU-T soundings if available or mandatory levels from constant pressure charts. So your constant pressure charts, the mandatory levels, when they send up a balloon for the SCU-T, the SCU-T is one chart, but they use that same data they plot on upper level charts. The constant pressure charts, the constant height charts, really, because that's what that is, the contours. The mandatory levels are like 1,000 millibars, 850, 700, 500 millibar, 300 millibar. There are certain mandatory levels that no matter what happens with that weather balloon, once it reaches that level, it reports data. It reports data at those levels no matter what. Anything else it sends in between that, any significant changes, then that's extra. So the mandatory levels are always going to be there. So stability, if we look at stability of two different layers, 850 to 700, we have the winds are backing with height. That indicates cold air advection. And from the 700 to the 500 millibar, the winds are veering with height. So that indicates warm air advection. So we have warm air over cold air. Now we are in a stable environment. So on the opposite end of it, 850 to 700, the winds are veering, indicating warm air advection, and backing, indicating cold air advection. Now we have cold over warm. That we have the cow. The cow is unstable. So that is a quick look at the SCU-T and the different layers. How you can tell if you have cold or warm air advection. Calculating the thermal vector. You don't really have to do that. Just once you get used to what backing is, the winds are going up into the upper layers, going counterclockwise, and then veering is if they are going clockwise, if that direction changes clockwise. So now, just by those and using two different layers of the atmosphere just on a scutee, because you'll have the wind chart on the scutee, the staff that shows all the different layer winds, and you can even pull out, you know, cold air advection at every level of the atmosphere up until you hit the tropopauls. So if you have a supercell, you're unstable completely, and then all of a sudden they let a balloon loose, something happens, change in the atmosphere, you have cold air advection going into the mid layers, you can have dry air entrainment, and that could just wipe your supercell out. So all that stability becomes stable. So I mean, obviously if you have cold air advection in the upper levels, then that air is going to want to sink. So how warm and unstable is this air? How much mixing are you going to have? So if you have cold air advection on the surface, which if you have high pressure pushing in, then that's just going to push down on all the moisture, squeeze it out, and you'll just dry out on the surface. So you can have an upper level, you know, thunderstorm, an elevated thunderstorm or tornado, but with the stable layer on the surface, is it going to, you know, hit the ground? So just a lot of little information you could get from these charts, the scutee, the upper level, and the upper level charts. On the scales, the mesoscale, we talked about these in earlier videos. There are like 4 different scales. Mesoscale, just kind of think of weather station with a radar. That area is going to pretty much be your mesoscale. The synoptic scale is going to be, if you're looking at a surface chart and you have a frontal system, that area for the frontal system, that's your synoptic scale. So the concept of thermal wind, extremely useful with single station analysis and forecasting. With one scutee sounding, you can determine the type and magnitude of the advection between all levels. So once you get into the if you have a scutee for that station, you can determine cold air advection, warm air advection, stability throughout the whole layers at that station. So it's great for one location. So if you're several miles away from a station that launches the balloon, then you need to kind of look at several of the scutees around that area to try to determine how stable you are in your environment, because it does change over distance. Synoptic scale, the thermal wind vector represents the orientation and strength of the mean temperature gradient in a layer. The thermal wind vector will be oriented parallel to the thickness contours. We covered that. In most operational weather offices, the type and strength of advection is determined from the 1,500 millibar thickness chart. So if you look at the thickness lines, how far apart they are, how tight that gradient is, that's what's going to determine that. And this chart is derived by subtracting the heights of the 1,000 millibar level from the 500 millibar level. So now you're getting the heights between the 1,000 and 500 millibar level that's reported on this chart. It's different from just the 500 or just the 1,000, and then that's going to determine the thickness of the atmosphere. And looking at that 540 line, that's where you determine rain, snow, that's your mixture line, your rain, snow line. So just one quick thing to use for that. And then your gradient, how tight that gradient is, placing the jet stream, and how much jet support that gives a surface system, something like that, you can see from the thickness chart. Like I said, we'll get more into the thickness chart in the next video. So I think that ends the show. Just remember, cold over warm is unstable, the cow is unstable, and warm over cold is stable. So I'm going to go ahead and pull up a thickness chart real quick and just cover a couple things, and then we'll end the video. So okay, so this is the 1,500 millibar thickness chart, and I customized mine to make it easy to read. Alright, so I have the cold air to the north in blue dashed lines for the lower heights, anything that's lower than the 540 decameter or the 5400 meter line, that is this rain snow line. So here's our 540 line. I do that in purple. And now anything north of that line would be snow, anything to the south would be rain, and anything along that line would be a mixture. So I got red to the south, indicating the warmer temperatures, higher thicknesses. So when the precipitation's falling through those higher thicknesses, it's going to be rain because it's going to melt before it hits the ground. Any frozen precipitation. Alright, so cold air to the north. Anything to the north of that purple line, any precipitation that falls will be snow. So if we look at right here in northern, just out south of Lake Erie, up here, northeast Ohio. Get that out of the way. That is snow being reported right there. Snow in Columbus. Snow in Michigan. So north of that line is snow. Anything to the south will be rain. I don't see any. There's some significant cloud cover. They're showing broken skies, overcast. Then to the south you start getting scattered into that high pressure center, clearing out. So we don't have any significant weather. So I really don't see any rain being reported. Not at this hour anyway, as far as this chart, when this chart was made. So that's pretty much it on the thickness chart. I mean, we got, like I said, that's your main thing you're going to look at on a thickness chart. Then you have the packing. Now we can say the tightest packing looks like right through here. That would pretty much place that jet stream. So right through here. So if we wanted to, let's turn this off for a second, and then I'll throw the jet stream over this chart just to give you an indication what a jet is. So let's pull the heights. Isotherms, lines of equal temperature. And then if we want, we could even put the station plots over that. And this kind of covers up what we're looking at. So now, if we look at this jet stream, we're pretty close on that thickness line. The thickness packing to determine where that jet was. So we're pretty much, there's 160 knots, 165 knots right there. Coming back up and then wrapping around, and I kind of keep that into that jet max because there's a 125 knot wind right there. So and then you can see where your long wave ridges, troughs, and then determine on where your weather systems are being steered to. So get rid of that, and we'd have to just erase this chart completely. But if you look at the we can't see the thickness lines, so everything's got covered up, but we were pretty close on that. So that determines where the jet stream is. You look at the low pressure systems, where these jet maxes are. They're coming out of a ridge, going into a ridge, out of a trough, into a trough. You know, that's a lot of indication of what those systems, those ridges and troughs are doing too. So that's pretty much it. I'm going to go ahead and end the video here. I want to say thanks for watching, and visit my website, meteorology101.com, and get your head in the clouds.